Welcome back to Lecture 12, Part 2, High Performance Computing Advanced Scientific Computing course. It's Lattice, Boltzmann, and CFD applications. In the first part, we had introduction and a review and background about the Lattice gas automata, LGA approach, and its model, HHP model and FHP model. Also, we talked about a scale scope, which was microscopic scale, microscopic scale, and the scale that between these two scales is called mesoscopic scale, which is relevant to lattice Boltzmann. So we will continue in the second part about the lattice Boltzmann method. Boltzmann equation. Boltzmann derived an equation for the change of the distribution of energy among atoms due to atomic collision and laid the foundations of statistical mechanics. Boltzmann was also one of the first continental scientists to recognize the importance of the electromagnetic theory proposed by James Clerk Maxwell of England. Regarding the history, unfortunately, it was a tragedy was Boltzmann did not live to experience the glory of his pioneering ideas. However, currently the Boltzmann equation and its method has a broad application, and it was successful idea. Boltzmann's theory achieved the deserved breakthrough and acceptance among scientists only shortly after his death, with the help of Max Planck and Albert Einstein. Therefore, regarding this is about the history of the scientists who made this idea, and it's successful. And now we will see how this idea developed and applied in the fluid dynamic area. The Lattice-Boltzmann method, its abbreviation LBM, its equation came from at 1872. He explored a probability distribution function based on the particle collision. Here in this slide, you see the figure from the collision step and propagation. That's what's happening. Indeed, there are three main steps: pre-collision, post-collision, and post-propagation. It's named the most important achievement in 19th century. The probability distribution function is f, which is quantity of particle at time t between location x and x plus p over m times dt, and with momentum p and p plus dp. Instead of the momentum p, velocity could be used, and they are in the same behavior. With external force F on particle, the momentum P changed to P plus dP and location from x to x plus P over m times dt. This is the fundamental about the collision. That's what happening because of the external force. And usually we will see there are some assumption it's required in the equation to be solved. A quantity of particles stay equal before and after the external force act peak out of the conservation if there was not collision. If collision happened, there will be different in quantity of the particle before and after the collision. So these two statements are making two categories term of the Lattice-Boltzmann method. Here the equation established based off these two statements. With collision, the probability distribution function, it will be like this, before and after the collision. And with the collision, the difference between them, it has another function, which is commonly in this term is called Boltzmann equation. If ignoring the external forces and normalize the mass to 1, so the P it will be equal to C. This means the velocity equal to the momentum. Then limit to C the set of vectors Ci, which is mean the velocity of a component that can be used to tile the entire space, such as hexagonal tiling. So this is the some assumption and some mathematics term to be used in the Lattice-Boltzmann equation. And let's take a look at the Lattice-Boltzmann method feature. Based on the Maxwell theory, it doesn't matter to study the individual particle behavior. Indeed, the matter is the ability to study the probability of particle availability. The probability distribution function is defined by PDF, which is currently used in many areas. In the Lattice-Boltzmann method or its equation, there are 3 independent variables: position, which has 3 components, time, momentum or velocity, which they have 3 components. Therefore, there are 7 variables in the equation. And the equation is established based on the 2 fundamental concepts, collision and streaming. When we look at the equation, we see in the one side there is a streaming and the other side is the collision. Indeed, P the external force and usually is assumed to 0 for particle view. So when the external force is 0, the equation converted to a simple structure, we can see it here, which is called the Boltzmann equation from 1872. Indeed, when sigma f is 0, there is no collision. This assumption is applicable in many areas, like very dilute fluid, very less density, which is mean very few particles, for knots and larger than 10 particles without interaction. The equation has not microscopic properties such as viscosity, heat transfer also. The statement is when F is changed via collision, PDF for particle is changed as a result of the collision. This is a fundamental of the Boltzmann equation. Therefore, since there are not a microscopic feature, it's required to make some math operation to extract this feature. Indeed, sigma f is based on the PDF, and f is a function of a particle behavior. To extract the properties from the Boltzmann equation is the conservative laws. And we can see here in this yellow block how calculating the mass, momentum and energy, and also about the flow velocity. Based on the conservative law, it's possible to extract this feature. The another matter on to solve the Boltzmann equation, it's the definition for sigma f, the function. One of them using the Maxwell-Boltzmann distribution, which you can see this equation here. F equal is a local equilibrium value for the population of the particle in the direction of the specific link. Also in 1954 there is a BGK operator which also used in this term to solve the Lattice-Boltzmann equation. The term tau in this equation is a relaxation term and it's related to the viscosity. Also, there is evidence that the equation of hydrodynamic for gas, the Navier-Stokes, can be derived from the Boltzmann equation. Therefore, all of these evidence prove that Lattice-Boltzmann equation is applicable, especially in the fluid dynamic area, and its scale which is based off the mesoscopic, and it's located between the macroscopic and microscopic scale, could help based off the statistic and average properties of the particle to define the flow characterization and the behavior. Now let's look at some specific advantage which came up from the lattice Boltzmann. It's make possible to have Navier-Stokes equation solution for incompressible flow. It has some advantage for the HPC because it has a fast solution and low cost. There is no stability consideration in lattice Boltzmann, as we know in the traditional CFD. It is required to consider the stability to be sure that equation has a consistency and convergence, but in the lattice Boltzmann there is not consideration in this regard. Navier-Stokes equation required continuity, but LBM does not. It's deal with the particle. The coding is very simple. The displacement in lattice Boltzmann is linear, which is different from the Navier-Stokes equation, and it makes it really simple than the traditional CFD. There are some limits on the lattice Boltzmann method. Modeling the gas liquid, that means multi-phase flow with density difference or high viscosity difference between the phases. Simulating streams with high Mach number is difficult, and modeling geometry with curved borders is limited. Regarding a specific application that it's not easy and sometimes is not possible with the traditional CFD, the porous media, turbulent flow, multi-phase, and reactive flow, which is made it too simple to use the lattice Boltzmann method there. However, the lattice Boltzmann has some specific modification when we're solving the problem, and still it's ongoing in the research, and there are many open areas to apply the lattice Boltzmann and assess its capability and some statement about it. Indeed, it's a class of the microscopic particle-based approach to simulate the fluid flow. They are becoming a serious alternative to traditional methods for computational fluid dynamics. So as we can see, it's one of the alternatives for CFD in some areas, especially when we have flow around complex geometries. To implement it in the parallel computing is very straightforward, and we can show the lattice solve the Navier-Stokes equation of fluid flow. These all advantage and some limit and the application make the lattice Boltzmann one of the interested methods in the computational fluid dynamics to be applied, especially regarding the area was not possible to solve in the traditional CFD, and also about the HPC resources. When we are designing a solver for lattice Boltzmann method and Navier-Stokes, we can see the difference here between them. In this table, it's summarized how the difference between them is working. Navier-Stokes it's second order partial differential equation, but in the lattice Boltzmann is discretized the partial differential LBM, which is first order of the partial differential equation. For the Navier-Stokes must solve nonlinear convection term, but in the lattice Boltzmann convection term is linear. In Navier-Stokes for incompressible flow, we must obtain the pressure from partial equation to be able to solve the equation, but for the lattice Boltzmann, the pressure obtained via state equation. In our stock equation, we need to investigate the CFL term and meet the condition to be sure that the solutions will be stable and converge. But in the lattice, Boltzmann is always 1. In the lattice boson, molecular interaction is simulated, but in the Navier-Stokes, it's not applicable. In the Navier-Stokes equation, we need the boundary condition, initial condition. However, in the lattice Boltzmann, still it's required to develop the boundary condition and one of the open research area. In the Navier-Stokes, iteration is required to be converged, but lattice Boltzmann is explicit and without iteration. This table summarizes the main term and the feature of these two methods in the traditional CFD and lattice Boltzmann method, and it shows how each of these approach has an advantage and a limitation, and why is still open research area and in the development for the lattice Boltzmann method. Now let's continue about the lattice Boltzmann and the computing. Firstly, we should mention that there are a different model for lattice Boltzmann method proposed. For example, for the 2-dimension, one of the most known method is D2Q9, which is used for 2-dimensional problem, and it has a 9 velocity component. And in this slide, you can see how it looks like. For 3-dimension, it's D3Q15, which has a 15 velocity component. Here in this slide, you can see the domain of the problem, how discretized based of the lattice Boltzmann approach. And each of the these meshes can be modeled with D2, DQ9, and it has 9 velocity component. Also, as we said, in the LBM, one of the issues is the boundary condition. Usually, we must determine the velocity distribution function in the direction to the fluid region on the boundary. Also, regarding the lattice Boltzmann derived method, there are some points can mention them, that LBM is the naturally applicable to compressible fluids and microfluids. However, in compressible fluid calculation, the number of the fictitious particle velocity must be increased as the Mach number increases. Similarly, in microfluids calculation, the number of the fictitious particle velocity must be increased with increasing Knudsen number. In general, when the number of the fictitious particle velocity is increased, the basic equation of the lattice Boltzmann cannot be formulated into perfect advection type difference equation. So the finite difference lattice Boltzmann is often used. Then, as we can see, there are some issues need to take into consideration when using lattice Boltzmann method. Regarding the heat transfer also, since the formulation is assumed as isothermal flow, but the lattice Boltzmann can also handle flows with the heat transfer. For this purpose, we must introduce a new velocity distribution function of a temperature field. Indeed, the two velocity distribution function can be then calculated simultaneously, which provide the velocity and the heat or the temperature. As we can see here also, it has some point need to be known before using the lattice Boltzmann. Regarding the computing, it is using the computing cost and the time, which is a matter here. Regarding the turbulence flow also, there are some points need to be taken into consideration, because usually the viscosity term should be available in the Lattice-Boltzmann equation, but in the turbulence, when the Reynolds number is getting higher, the viscosity should be reduced, and in somehow we can say in the some range of the turbulent flow we don't have the viscosity term. This is some technique need to be used to impact these change to the equation. Let's start with the first example of the Lattice-Boltzmann application. It's the performance evaluation of Lattice-Boltzmann method for fluid simulation on A64 FX processor and supercomputer. In the middle of this slide, you can see a figure presenting the different performance of a different model of the Lattice Boltzmann, D3Q15, D3Q19, and D3Q27, and the number of the core increased. Based on the result, we can see it's using only OpenMP thread parallelization from 1 to 48 cores. In the case of the D3Q15 and the D3Q19 model, the performance improved up to 24 cores, and the performance levels off or slightly decreased when using a large number of the cores. But for the D3Q27 model, the performance improved up to 48 cores, and the performance on 48 cores is 432 gigaflops with 77 and 14% parallelization efficiency. Indeed, in this figure, the hollow marks show the performance when allocating 4 ampere processor per node using OpenMP plus MPI. For all velocity models, the OpenMP plus MPI version showed higher performance than the only OpenMP version, which shows the successful of the application of the Lattice Boltzmann and its effective result. Also, in the second figure, in the right hand side, we can see the performance again with number of nodes here, which the same these three models. It shows the weak scale performance. The dotted line indicates the ideal scalability. The weak scaling results are almost perfect for all velocity model. As in the single node performance measurement, the D3Q15 model had the highest execution performance, achieving 10.9 petaflops with 16,384 nodes. Also, the ratio of the inter-nodes communication time to total computation time is 6.6% for the D3Q15 model, which is mean 5.6% for D3Q19 model, and 4.9% for the D3Q7 model. The communication cost is relatively small, and both D3Q15 and D3Q19 model send and receive 5 distribution functions to and from one neighboring region. So this is a very summarized and short description of the result when we are using the model from the Lattice Boltzmann method. And from this example, we can see their capability. It seems for the speed up, they can have a good performance, and these example present these difference of these three model D3Q15, D3Q19, and D3Q27. The another example is sedimentation of an elliptical cylinder. This is one of the basic examples of moving boundary flows that can be simulated in the lattice Boltzmann. Indeed, in this example, an elliptical cylinder with measure and minor axis length of A and B settles under the gravitational acceleration g in a stationary fluid. Indeed, as you can see in the figure of this slide in the left hand side, when we look at the domain, the fluid fills a channel between parallel plate of width h, as you can see. To use the lattice Boltzmann method, the computational domain is divided into a square lattice with lattice spacing delta x. H is set to 200 delta x, and the channel length is 17.5 h. So with these lattice spacing, the domain is divided. Also, there are some other boundary condition properties of the fluid, and also the initial position of the cylinder, which is beginning to start. All of this setup has been done for this solution. When we look at the figure in the right hand side, the upper one, it shows the flow field around the falling elliptical cylinder. It also mentioned that during the fall, the elliptical cylinder oscillates in the horizontal direction while separated vortices develop behind it. This is one of the phenomena that can be seen in this simulation. One of the terms that mentioned in this study in the result, which they are lower in this slide in the right hand side in this figure, the result of the calculation of lattice Boltzmann equation, which count for the internal mass effect, are almost coincident. The result of the calculation, which ignore the internal mass effect, significantly differ from the other result in terms of both frequency and amplitude of the oscillation. This means the internal mass exerts a significant effect on a steady moving boundary flows. So as we can see, using the lattice Boltzmann for this kind of problem could provide the proper simulation with the remarkable result, and we can study and understand such phenomena with good detail. And here we finished this lecture 12, Lattice Boltzmann and CFD application. In the end, there is a video. It's presenting introduction to the lattice Boltzmann method, and you can see visually what we talked about the microscopic, mesoscopic, and macroscopic scale and their difference, how we extracting the properties in the macroscopic from the domain of the problem, and from the microscopic we are using for the particle, and mesoscopic is between these two areas using the statistic. I suggest you watch this video and you can see interesting visualization of this scale. The link for the YouTube videos is available in the references, and you can find them and you can watch them. And thank you.